All right, it's 7:05. I think we should get started. Well, it is my pleasure to introduce Dr. Bill Power, as he is the chair of the Department of Chemistry, and he's going to introduce other panelists. So I really hope everyone enjoys this event, as it is our first Sci Talk for Chemistry.
Thanks very much, Eric. And I want to welcome all our alumni and friends tonight. On behalf of the Department of Chemistry and the Faculty of Science, it's great to share this event with you. Before I get into some remarks to open up tonight, I do want to give the acknowledgement from the University of Waterloo. The University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated on the Haldimand Tract, the land promised to the Six Nations that includes 6 miles on each side of the Grand River. Our active work toward reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within our Indigenous Initiatives Office. As you can see, I am back on campus. I am in my office, which you can tell from the clutter behind me. And I'm glad to say that we're back after such a long 20 months we have had. At this stage, it seems surreal to think back to March 2020, when all we did ground to a halt, and we were all forced onto platforms like this. For how long, no one knew. 2 weeks, 2 months, now almost 2 years. But we worked hard and learned a lot through the process. We gained new tools and new approaches to old challenges, and found ways to keep our campus and each other safe. Since June 2020, we have been reopening our research labs. And since September 2020, we have reopened many of our teaching labs. We found new ways to do things online, and one advantage of those tools has been the ability to reach out to our friends and alumni more regularly than before. So thank you for joining us tonight in one example of that. But in addition to those new lessons of the online world, we also realized, again, the critical importance of hands-on experiential learning in chemistry and in science. That's not new for the university that invented co-op education, but it's always important to emphasize the skills and learning that come from doing things for yourself, from planning ahead and managing risk and seeing experiments through. As we look ahead to the winter term and beyond, we know we will be fully back on campus next term, and we have new energy and new ideas to take our programs and our students to new heights. That's why we have launched a new tool, our Chemistry Program Activation Fund, to support new investments in our programming, our infrastructure, and our equipment, to ensure our learning and our experiences remain at the leading edge for our students. This fund will be the focus for Waterloo Science next week on Giving Tuesday, and we have several fundraising challenges in place to entice and encourage you to find a way to support us and our plans through this fund. More details are available on our website, and look for more messages from Waterloo Science in the days ahead. But in the meantime, let's turn our focus back to our plans for tonight. I want to start by introducing our host and moderator tonight, Dr. Alan Vio. He's a successful chemistry PhD alumnus from Waterloo's class of 1984. Alan has over 30 years of experience in the management of the science, information technology, and creative arts sectors. He worked 18 years in the private sector for companies such as Hewlett-Packard, Corel Corporation, and Xerox, and finished off his professional career spending 15 years working at Health Canada and other federal government agencies. Alan, I want to thank you for taking on this task tonight. It's good to see you again, and I'm pleased now to turn things over to you.
Thanks, Bill. It's a pleasure to be here this evening, and always good to talk to Waterloo alumni. It's interesting. I always carry a University of Waterloo notebook in my bag, and a number of people say, "Oh, you're a Waterloo alumni." Yeah, and it creates this instant bond that we have among us. And I wanted to give a little story why I chose University of Waterloo. Back in 1980, I finished my Bachelor of Science at University of Ottawa in biochemistry. And I'd spent a summer research assistantship at the University of Waterloo between my third and fourth year, and absolutely was totally enthralled with the university's innovation and practicality kind of mindset. And that really brought me to why I went to University of Ottawa and to Waterloo, and why I want to support it moving forward. I am a monthly donator at the Program Activation Fund, and I encourage everybody to do so, because that's what's going to help us continue this drive to being innovative. But so this is what we're trying to bring today. Is we're going to highlight a few people that have taken their degree from the University of Waterloo and have forged ahead into some innovative and interesting stuff. Not just we'll talk about their cool science that they're doing, but also I want to find out a little bit more of what got them there and why they're there. So we're going to do that. But first, I want to test out, Eric, if I can, we'll go off script a little bit, our Q&A. One of the things that I kind of do on the side is, you'll see here, can you guess? I'm Santa. So the University of Waterloo alumni is Santa. How's about that? So you can see in this shot that was taken 2 weeks ago, there's some snow in the background. It is artificial snow. Can you tell me the chemical that makes up this artificial snow in the Q&A? How's that? We'll give you bragging rights for that in a minute. Well, I'll probably reveal what it is, or the winner. Can we see the Q&A? Is that possible? Just testing it out. All right, so we'll leave that at that. But so if you want to throw it into the chat, that's okay too. We'll monitor that, and I'll let you know after our first speaker. Our first speaker I'd like to welcome is Marej Beg. He's an innovator in life sciences with 8 years of experience in biological sensors and diagnostics. He co-founded Medela Health and was the Chief Scientific Officer from 2013 to 2020, assisting the company with developing the world's first non-enzymatic, in other words, solid-state sensor, capable of detecting glucose in neutral pH media. Currently, he serves as the Chief Scientific Officer at Spectra Plasmodics, where he leads the Research and Development Division in designing Raman spectroscopy solutions for point-of-care settings to overcome the many problems facing our communities. So Marej, would you introduce yourself, and let's take it away.
Hi, everybody. It's a pleasure to be here. I'm really looking forward to answering any questions that you guys may have and connecting with the alumnus community. So I graduated in 2016, and honestly, I haven't been able to tap into the alumnus network as much in Waterloo, and I'm really excited to get to meet all of you. Alan, are you good to share the video? Okay, I think it's going up now. Hello, everybody. My name is Marej Beg. I'm so happy to be back here to speak to each and every one of you as a very proud Waterloo alum. I graduated in 2016 from the biochemistry co-op program. In my second year, I started my first company called Medela Health for profit to develop tools to help with diabetes management. After 8 years serving there, I moved over to Spectra Plasmodics to help them scale their R&D. Today, I'll be speaking to you about Raman spectroscopy and its use in fighting the opioid overdose crisis here in Canada. Our communities in Moncton, Victoria, Kingston, Toronto, and even in Waterloo are facing a very dangerous crisis. Adulterants are being mixed into the drug supply. These adulterants are present in trace quantities, but that's enough to overwhelm our bodies and trigger a fatal response. Deaths are occurring because of synthetic opioids. Opioids are a class of medication used to treat many different types of pain. Opioids can be weak or very strong pain relievers, with one of the strongest, fentanyl, being 50 times more potent than the weaker heroin. The number of opioid-related deaths in this country has risen drastically, with 6,265 in 2020. To put this into perspective, in 2018, the leading cause of death in this country were the big two: cancer and cardiovascular disease, with diabetes and Alzheimer's at the bottom of the list. In only 2 years, opioid overdose deaths are rivaling diabetes, and this year is projected to overtake diabetes with a 65% increase in 2021 in comparison to the same time last year. In response to this crisis, our government has introduced safe consumption sites, with medical staff on hand for safe administration of illicit drugs with no legal repercussions. The goal is harm reduction, which is the idea that there is harm that comes from psychoactive substance use, but the people facing the substance use disorder do not need to be free from substance abuse in order to receive care. The fact of the matter is, fentanyl mixtures have skyrocketed across North America. It's costing us $15,000 in our ER for those who survive. Labs take months to confirm whether an adulterant is present. Lastly, our sites are ill-equipped to measure these trace adulterants, especially when the adulterants keep changing. This is where Raman spectroscopy comes in. You may remember hearing about Raman spectroscopy in an undergrad chemistry lab. When light is shined at a particular molecule, a portion is either absorbed, reflected back at the same wavelength, or it undergoes a shift. The degree of shift depends on the chemical bonds present in the molecule. A C double bond and an amide bond have different degrees of Raman shifts. Using Raman, we can observe vibrational rotational modes in a molecule, producing a unique chemical fingerprint. Raman spectroscopy is a broad spectrum technology which can detect multiple targets using information inherently present in the molecule. It works great with samples dissolved in water, since water does not have a very strong Raman spectrum. An example Raman spectrum of acetaminophen is shown here. Now I want you to pay particular attention to the phenyl group, as phenyl is one of the most Raman active functional groups, with the peak occurring around 800 to 1000. We will be using fentanyl in this example. Now let's take a look at the Raman spectra of fentanyl. How do we know that the phenyl peak occurs actually at the 1000 Raman shift region? Well, here's a simple experiment. We'll be using a technique called isotope editing to replace the hydrogen in the lower phenyl group with heavier deuterium to create fentanyl D5. Now let's see what the spectrum of fentanyl D5 looks like. Isotope-edited molecules show red-shifted Raman bands due to a higher mass of deuterium relative to hydrogen. Frequency of vibrational modes is highly dependent on relative mass changes. We observe a third peak, but why didn't the previous peak disappear? This is because the fentanyl D5 molecule still contains one unaltered phenyl group. Lastly, let's take a look at equal parts mixture of both fentanyl and fentanyl D5. Notice how the middle peak has a much higher intensity in sample in comparison to the fentanyl D5 sample. This is because between fentanyl and fentanyl D5 there are 3 unedited phenyl groups and only 1 isotope edited group. Is this enough evidence for you to be convinced that the 1000 peak is phenyl? For the spectras we just observed, all fentanyl was present at a low concentration of 10 parts per million. Without a special technique to enhance the signal, no peaks could be observed using normal Raman. This is because normal Raman produces a relatively weak signal, and a method is required to enhance the sensitivity. For this reason, a special technique referred to as SIRS is used to create a nanostructured surface, which the analyte can bind to, and is based on oscillations of molecules in proximity to this surface. The method enhances the signal mainly through electromagnetic interaction of light and the metal and analyte. The figure shows a probe molecule measured using normal Raman at 1 millimolar concentration. Even when it's diluted more than 1,000,000 times, the SIRS technique still produces a higher signal. Our workflow involves 3 easy steps of taking the sample, mixing it in a solvent, placing a drop onto a SIRS chip, and reading it with a handheld Raman reader. Science can be very complicated to develop,
but its use should never be. That's why creating easy-to-use workflows is integral to our work in merging science with usability. We are working very closely with several safe consumption sites to get these tools in the hands of those who can use it the most. Remember, this is not the end of the crisis. We have a long road to travel, but perhaps this is a meaningful step. Thank you for listening to my SciTalk. I want to leave you with this. I started on this path because I love building. Big, small, often useless, sometimes meaningful, each and every project brought a new perspective. I ask you this. My support was the Waterloo community around me and the mentorship I received by a few key people. Get involved in projects. My door is always open for our people. Mentorship, project involvement, general advice. Here's my Waterloo email address. I would love to hear from you. Thank you and take care.
Well, I tell you, that's pretty cool stuff. Being a spectroscopist myself, I just was really geeking out on that. I love that, So that's that's great. So, Marius, can you tell me, like you had intimated a little bit about that you liked to, tinker with stuff. Can you expand more about how that's led you from when you graduated to where you are now?
Yeah, absolutely. So that first started when I took part in the co-op program in my first year. So I was working at Environment Canada at that time at the Inland Water Center down in Burlington. And I love the work there. There was a lot of analytical analysis that we performed on a daily basis. But what didn't happen during that time was I didn't get to draft my own hypothesis. And so shortly after I came back from that co-op term, I got involved in a project. That project ended up becoming a company. I ended up developing technology for that company, which allowed them to raise a lot of money. And this is when I was introduced to this art of creating technical narratives or stories that attract commercial investor interest. And it just sort of kicked off from there. And yeah, and now I'm basically doing that same thing for a living here at Spectra.
So that's an interesting aspect. I want to expand on that. Is what I
Yeah.
mentioned earlier is that the science at Waterloo is great, and then what's interesting is the whole culture of innovation and practicality. And it sounds like you've gone down that road. You've gone down the let's marry the business side with the science side. And how
Right.
did you find that transition?
It was honestly very natural. So Waterloo has a certain uniqueness about it that allows it to be very easy. So first of all, Velocity, an amazing program tailored towards, custom made towards entrepreneurs. The sentiment is that it's not odd to take a different path, such as entrepreneurship, to want to do your own thing. Waterloo's open IP policy, which makes it extremely easy to own your own invention when you work on something. The welcoming lab community. So when I got started, I was working with the professor in QNC, and he was in the chemistry department at first, and we saw the transition from chemistry to QNC building, and he was very welcoming, and he allowed us to use all his equipment and his space. Not only that, any existing infrastructures that are typically only accessible to academics, we got to have access to, such as the QNC facility and the facility run by Vito. Not only that, the community in Waterloo in general, especially the law firms, they really catered and allowed us to basically file for patents and be able to get contracts for low fees. They cater to younger companies. So I think the entire ecosystem is just wonderful.
So we have a couple of questions. Remember, people, you can post your questions in the Q&A section instead of the chat, please. But I'm monitoring both. So one of them that we have here is, how big a quantity or sample would you need to make an accurate detection? Any barriers to small sample sizes?
So the quick answer is no, not really. So the amount of sample that we usually recommend is about 10 milligrams, which is a very small amount. Typically, folks who bring in samples, they want to consume these samples at the end of our analysis. So we don't want to take too much sample, because at the end of the day, it is still intended for their personal use. So about 10 milligrams, we can get away with less too. It's a very ultra trace detection technique, so we can detect very, very low amounts with very little sample. Yeah.
Great. We also have another one. Is Raman susceptible to Fourier transform like IR?
Yeah, there is an FTI, a Fourier transform Raman technique out there that's it's mainly accessible in the labs. It's useful for basically studying multi-level components, and it's just at the moment it's not field deployable from my understanding. So we're just sticking with the normal Raman, which is enhanced with SIRS. Yeah.
Okay, very cool. All right, thanks, Eric. Anybody else have any questions? Please keep them coming. We'll have all the panelists at the end as well, so we can answer more questions there. But let me answer the question about the artificial snow. So everybody was wondering what that is, right? Well, ladies and gentlemen, it's called Snow Wonder, and it is made of sodium polyacrylate. There we go. Here's the formula for it. All right. And this is a product that's been around for a long time. It was originally, this one was designed for the artificial snow in Japanese indoor skiing areas. It's also used in diapers and sanitary products where a lot of water needs to be absorbed. It can hold 20 times its weight in water, so it makes it very snow-like, and is commercially available and is non-toxic. And there you go. All right. Thank you, Mirage. We'll move on to our second panelist. I'd like to introduce Patrick Deep. And Patrick was involved in a number of activities in clubs during his undergrad at Waterloo, most important being the UW iGEM team, where his involvement has continued as an advisor, mentor, and competition judge for the iGEM community. Patrick is founder and program director of CSBERG, the Canadian Synthetic Biology Education Research Group. He is also co-founder of Liretta, a startup engineering reusable 3D printable growth media to help hydroponic crop farmers reduce their waste. Patrick balances both of these roles while completing a PhD in chemical engineering at University of Toronto, where he is recently recognized for his research, placing third in the 60th Conference of Metallurgists. Welcome, Patrick. How are you doing?
Amazing.
Great. We'll have your video and we'll come back to you.
Hey everyone, my name is Patrick, and I've been working with biology for like a decade now. Right now what I'm doing is studying and engineering metalloprotein systems to be able to treat mine effluent from Sudbury, for example. And in this entire process, what I've become as a specialist is someone who specializes in applied bioinorganic chemistry, basically. But the thing is that during my PhD, I created a startup called Indus with one of my co-founders, Adnan, where I had to now become a generalist. Specifically, I had to learn how to create a business plan, pitch a pitch deck, talk to customers, all these skills at a general shallow level, but just enough to be able to pull off a startup, which is now allowing us to be able to design and manufacture grow media for hydroponic operations. And in my training, I've been trained as a specialist quite well, but trained as a generalist, specifically a generalist synthetic biologist, was not something I was trained for. And this word training is very important to me, specifically education. So I founded a nonprofit called Canadian Synthetic Biology Education Research Group, CSBERG, and it's here we ask, how do you train synthetic biologists? Because in the future, universities will have to create synthetic biology programs and course series to be able to create these practitioners to go out into this growing field of synthetic biology. So at CSberg, we are thinking a few years ahead, into the future. So we formed in 2019, and the first project we did to inform what we're going to do as a group was survey 17 Canadian iGEM teams. iGEM stands for International Genetically Engineered Machine. And we wanted to understand what the synthetic biology education landscape was at that time. So we did a qualitative analysis of these surveys. And what we created from all these insights was FTSB, the Framework for Transdisciplinary Synthetic Biology Education. And there are 4 design principles that we discovered in this survey that are important for developing future synthetic biology curricula. Namely, knowledge domains, collaborative learning elements, coherent course objectives, and having students be working in learning environments that simulate real-world scenarios, whether in grad school or in industry. So since the analysis, we've submitted the manuscript and published it recently in the Canadian Journal of Microbiology. And now that we have, the FTSB, we wanted to ask ourselves, like, how do you actually implement these design principles? And so we had prepared these YouTube videos that we were deeply dissatisfied with, that we then created 2 courses called SYMBI 1 and 2. These are online courses delivered over Zoom, which we've now taught to over 125 students across 4 modules at U of T, with so much data that we're actually partnering with OISE, some of their PhD students specifically, to help us process this actual data and prepare a manuscript to submit to CBE Life Sciences. Now, in this entire process, we have instructors that have been working for a year plus on this project who now have the leadership skills to complement their teaching skills, which we've now promoted to these new positions to develop the core and advanced programming, we call it, to be delivered in summer 2022. We also have a high school project doing the exact same kind of work. How do you design a curriculum that implements these design principles to teach high school students synthetic biology? And all of this, again, relating back to generalists and specialists, we're thinking about how do you create a curriculum where there is clarity in how students can go through these courses, this program, to become a synthetic biologist that is specialized in one area, or become a generalist that's able to work in different parts of synthetic biology. Thank you.
Again, interesting conversations we're going to have here. First of all, Patrick, I'm an old guy. You're going to have to explain to me what synthetic biology is. So can you tell me in simple words?
Yeah, it's kind of like the next wave of biotech and that we're familiar with. So pharmaceuticals, GMO crops, for example. You can consider synthetic biology the next wave where we bring in much more of the engineering design principles and mathematical concepts to be able to understand biology, but also redesign things at the molecular level, rewire cells to be able to do things they don't normally do with a lot more precision, or at least we try to have more precision.
Great, that's cool. So let's go back to CSberg. What are the courses going to look like, and who can take them? That kind of thing.
Yeah, the courses are intended to introduce students to synthetic biology. So we don't go into mega depth on metabolic engineering. We provide introductory topics across the field. So students will have opportunities to work with other students in very different programs that they don't normally work with in the same course. And all of this, they're working towards one design challenge that we're developing with some startups in the synthetic biology space in Canada.
So you can say it's kind of like a hack group, right? Where you all get together and try to solve a problem.
Yep.
And that's pretty cool. So now we talked about generalist skills, and I, when I hear this, what you're talking about, synthetic biology, I mean, you're manipulating things. Does the topic of ethics ever come up in this?
Yeah, ethics is integral in this because we've learned from the GMO crop debacle with Monsanto that to do these kind of things with minimal stakeholder engagement affects your solution space. It affects what you're able to actually design and test. Whether or not it's actually good economically and socially, it doesn't matter if you can't communicate that to the public and gain their trust and feedback. So in this new field, synthetic biology, a lot of these younglings, I guess, these younger students going into the field, they are like part of their like training in this competition, for example, is to think of the social sciences behind their work.
Great. We have a question. How do you identify generalists if you're hiring people? It's not something you put on a resume and say, I'm a great generalist, you know? So how do you look for those skills?
Yeah. I mean, definitely like a Wikipedia or like a Google search of like specialist versus generalist. Like everyone has their own definitions of these things. And a generalist isn't someone who doesn't have specialty. I'll point that out. Like, I think it's important that all students gain this specialty so they have something that they've mastered the craft of, so they can actually have employment and gain wealth. But a generalist is someone who, you know, instead of like doing a classic PhD where you go really deep into, for example, studying one protein in every single way possible, they allow themselves to be a bit broader, and they'll learn those skills that they don't normally learn in these traditional PhDs, such as business skills, communication skills, and project management. So I think if you're looking at a resume and you're asking yourself, is this person a generalist? Look for like how much time they've put into specific extracurriculars, like a startup or like a design team. If they've done those activities, it's a clear indicator.
So similar to Mirage we were talking about earlier, you've moved from very technical into trying to marry the business world. How has that experience been for you?
Fun and challenging. Fun because I mean, the PhD, you have successes and failures, more failures than successes, and you know you kind of need that like positive stuff to kind of bring you back up. So the startup definitely does that, but it's challenging doing a startup during your PhD because your professors, 4 of them, require you to get more specialized. But at the same time, you have these investors and this incubator that kind of pushing you to learn new skills about how to run a business and start one. And so those two conflict all the time in my head. And that's why I've said in the past to our group of panelists that like I'm constantly in chaos because there's this interplay between the two. But I think in this interplay, you find that balance, and that balance is where you learn the most.
That's a good point. That's a very good point. Thank you. We'll move on to our next panelist. I'd like to introduce Michael McCracken. And Michael is a 4th generation steelworker with Algoma Steel in the beautiful city of Sault Ste. Marie, Ontario. He graduated from Honors Biochemistry program, where he began his career with Algoma as a development chemist, quality assurance and technical services, and has progressed over the past 16 years to become a process specialist. Michael is a proud UW alumnus, and while his work today is outside of laboratory settings, it was the biochemistry program that provided him with the analytical tools and critical thinking necessary to be successful in the steel industry. Let's learn about Michael in this video.
Good evening, everyone, and thank you for tuning into SciTalk's Chemistry Edition. My name is Michael McCracken, and I graduated from the University of Waterloo in 2002 with an honors degree in biochemistry, biotechnology option. I'm a process specialist at Algoma Steel in the Coal Mills Technical Department. I would first like to thank the Faculty of Science at the University of Waterloo for inviting me to speak as a SciTalker. I am truly honored to be on this panel, and I hope that each of you from around the world will be able to take something positive away from this event. I was born and raised in Sault Ste. Marie, Ontario, Canada, which is where my wife Megan and 2 children Matthew and Max call home. Megan is also a UW Faculty of Science graduate, and we met under the link. Growing up as a child in the Steel City, commonly referred to as the Sioux, I was surrounded by family that worked at Algoma Steel. My great-grandfather, both grandfathers, my father, and several relatives retired from the plant, but none of them had a formal university education in science. So when I chose to study biochemistry, I did not anticipate or plan on becoming a 4th-generation steelworker. I remember talking to one of my professors, the late Dr. Carrie Bissonnette, about how fascinating and intricate the world of science is. He reassured me that UW would prepare me with practical skills. I believe my career on a high-paced industrial floor demonstrates how I've been able to apply theories, principles, and scientific methodology that I learned at UW to identify opportunities for improvement, resolve problems, and help my company thrive in a very competitive and demanding market. Algoma Steel has been a fully integrated Canadian steel producer since 1901. We proudly manufacture a full range of hot and cold roll steel sheet and plate products. We supply steel to automotive, construction, infrastructure, energy, defense, and manufacturing sectors. We are a key supplier to the National Shipbuilding Program, Henvey Inlet Wind Tower Project, and produce steel for the Blue Water Bridge, Rogers Center, and Pearson International Airport. Our armor plate was used in the military and Sault Ste. Marie's Tactical Transport Unit. From these diverse examples, I am sure you can appreciate the importance of science and the chemical composition of our steel. For more than 16 years, I have been very dedicated and passionate about the steel industry. I will always remember my first day, lacing up my work boots, driving onto the property wide-eyed, and walking down a long corridor to the chemistry lab in steelmaking. I took a moment to reflect on my family, friends, and education that helped me get to this position. I felt confident that UW had prepared me for this opportunity to work with analytical equipment in a chemistry lab. Working as a development and senior chemist, I was responsible for calibrating and maintaining statistical control of our optical emission spectrometers and combustion instruments to ensure quality assurance. Our chemistry lab tests samples to ensure we have the specified chemistry not only on our final product, but also throughout iron making and steel making processes. Maintaining standards and providing accurate information to our team is critical and extremely time sensitive to ensure we are treating and refining our liquid steel with the required amount of alloys. Understanding properties and the periodic table of elements is imperative. We use X-ray fluorescence and combustion equipment to perform elemental and compound analysis of lime, iron ore, coal, coke, and slag samples. We use gas chromatography and wet chemistry techniques to test light oil, tar, and coke oven gas for aromatic compounds. Ensuring WHMIS and laboratory safety measures is a requirement and priority to protect our employees and the environment. I left a laboratory setting to apply my knowledge and experience to manufacturing and supply chain management. Being able to apply the same methodology and critical thinking that I learned at UW helped me grow, understand, and impact our business, identifying trends, patterns, and utilizing technical tools to improve our manufacturing processes and exceed our customers' expectations. It was evident that I was taught to adapt and possessed the ability to learn. My role in inventory management required an in-depth knowledge of the chemistry of our different practices to ensure our products met the intended grade and specifications of the end user. Again, critical thinking and the ability to make important decisions ensured my success and the company's strategic objectives. In 2018, I joined the technical department as a process specialist. I have been able to work with my colleagues to significantly improve our products and processes. We have altered and improved the chemistry to make stronger and more resistant steel. I've spent the last few years dedicating much of my energy and focus to our batch anneal facility. It requires me to understand and apply thermodynamics, the effect of annealing temperatures on microstructures, tensile behavior, and to apply both Six Sigma and scientific methodologies. At Algoma, we are always improving, developing new grades, increasing capabilities, and looking forward to further transforming our business. Led by our CEO and fellow UW alumnus, Michael McQuaid, Algoma Steel is investing in its employees and our processes, optimizing and modernizing to become a more sustainable steel producer. We are moving forward on a $700 million transition into electric arc furnace steelmaking to become a leading producer of green steel by significantly reducing carbon emissions. To be successful in this journey, they are not only investing in my colleagues and I, but they are recruiting and working with academic institutions to continue our legacy in Canada. I've been very fortunate to be able to travel on business across North America to meet with customers, suppliers, service providers, competitors, politicians, and attend steel conferences. Whether you are a current student, recent graduate, or already well established in your career, I believe it is essential that you build relationships, effectively communicate, collaborate, and embrace diversity. The future is bright for Algoma Steel and the University of Waterloo, as we are both leaders in innovation and developing the next generation of steelmakers and scientists. It is great to see the Faculty of Science hosting events like this to further develop and provide past, present, and future students with examples of different career opportunities. I am forever grateful for the bonds I created at UW and to my family and friends for helping me cope with the challenges of university. The countless hours of classes, labs, research, and studying provided me with a foundation of different learning styles, the work ethic, and the ability to prioritize my time required in an industrial setting. I find science and the steel industry fascinating. I encourage you to never underestimate the possibilities that a degree in science from the University of Waterloo will provide. Be curious, be engaged, be data-driven, be a warrior. I look forward to any questions you may have. My contact information is provided, so I welcome you to connect with me on LinkedIn, send me an email, or pick up the phone and give me a call. Thank you for your time.
Michael, fascinating. The steel industry, as you said, you're fourth generation in there. It's been around for a long time. And, quality assurance is also one of those underrated chemistry things that you see around. But one of the things that you just mentioned right at the end is the importance of data-driven decisions and improvements. And I just can't help to think that, all the training that you've got from the QA part really helps build that foundation to do data-driven decisions and process improvements. Can you comment on that?
Absolutely. Data is so important, and where you get the data from is also equally as important. So our company has invested a lot of money and time into artificial intelligence to help us gather that data quicker. We've upgraded our systems to an SAP-based system, which is, again, easy to grab the data that we need so that we could spend more time resolving the problems as opposed to sitting behind a computer and going through the data. So we're a data-rich company. We have years of data, and as we continue to transition into the next phase, it's going to be that much more important that we gather data, look at it, analyze it, and make important, quick decisions.
The other aspect, of course, about the steel industry being so old is that it's been mostly male dominated. You talked about diversity. Can you expand on any opportunities for women in the industry?
Yeah, I think it's very important that we continue to advocate and bridge that gender gap in manufacturing. I strongly encourage more women like yourselves that are present to explore and pursue opportunities in the steel industry and manufacturing sector as a whole. Algoma Steel has been very proactive in promoting women in steel. We recognize that a diversified team delivers more positive outcomes. Prior to COVID, Algoma Steel hosted and provided tours to steelworks of 100 young women as part of Canadian manufacturers and exporters initiatives. The goal was to provide greater context to women about what goes on behind the walls of an advanced industrial facility like Algoma Steel. While women make up half of Canadian workforce, they represent less than 30% of the manufacturing workforce. So globally, we need to continue to break down the barriers that women face. Collectively, we need to ensure that women are empowered to pursue a career in science, technology, engineering, and mathematics, the STEM fields. So diversity in our teams is critical to our future success. Some of my brightest colleagues are women, from metallurgists to shift coordinators to application and process specialists to the general manager of the cold mill at DSPC and my general manager. So we're fortunate in Sault Ste. Marie to have inspirational leaders like Dr. Roberta Bondar, Canada's first female astronaut and the world's first neurologist in space, to help break down some of those barriers that women face locally and across Canada. So thank you for the question.
All right. So we have a couple of questions from our viewers. Where does Algoma get its iron ore these days?
It's hard for me to answer some of these questions because I don't own the rights to, publicly speak about what contracts we do and do not have. So I have to sort of turn to take a, I don't want to say a pass on that one, but I do have to be careful on what I disclose. So.
Well, okay, so
Hopefully
it's a
that's
global
okay.
supply chain, right? Let's go with that one.
Hopefully that's okay with the
I guess that because
and go from there.
the viewers, they had a co-op job at Algoma Ore Division in Wawa in 1975. So that's where that question came from. So another one is, does Innovation Algoma come from internal R&D only, or does it outsource or collaborate with external parties like academic labs?
No, I think that's actually important. We do have an R&D department and a strategy group that leads where we're going in the future. And we do turn to partnering with academic institutions through co-op opportunities. And I think it's, Algoma Steel's focus on the future. And they have a responsibility as an organization to foster relationships, to generate highly skilled jobs in science, technology, engineering, math, like I mentioned before. We are collaborating, and we help students access innovative technology, gain valuable hands-on experience, and to adopt these emerging technologies. So I've worked with a lot of different summer students and graduates in training. And it's great to see a diverse group of people. So yeah, I think we do, I've personally done some work with Western University at the Surface Science Center there to get some of, more in-depth technology that we may not have on site. So typically, if we have the technology on site, or the engineers or scientists or stats people to evaluate it, then we'll do it ourselves. Otherwise, we have no issue with outsourcing and collaborating with local academic institutions or institutions like we're doing now with Waterloo.
Great. So I'd like to invite all the panelists to come back on, and we'll have a general session. I think that the theme that I've heard was, again, this idea of technology innovation, marrying that with practical business skills and going to market skills. And it seems to be a theme that comes through all three of you speaking. Do you have any thoughts on that? I'll start with Marich. How about you?
Yeah, absolutely. I think science, for me, it gives me meaning when I know that there's an impact that's being driven from the work I do. And I try to keep I guess that's why I love creating narratives, because you get to create narratives for someone, and that someone usually has a specific particular need that they want fulfilled. Honestly, it just makes the science way more impactful. If all the players in the supply chain, everybody who's involved in the innovation is benefiting. So yeah, it's to me, it's instrumental, but it's not an easy thing to do. I think as an individual, you have to develop your situational awareness skill to be able to see across all these realms as to see what everybody's about and what their challenges are. So it is difficult thing to do, and many people ignore it for that reason. But I think that's the only way that we're gonna push boundaries. We have to be able to do that.
Great, thank you. Patrick, any of your thoughts?
I think the problems that we face moving forward are quite complex. Climate change, specifically pollution. In short, I think because these problems by nature are very complex, you can't have one person with one area of knowledge figure out a way to just solve it. You need to have a team of many people contribute knowledge to be able to solve these complex problems. And just by nature of that, it's important for students to be trained to be ready for this kind of collaboration, because collaborative skills is unique. It doesn't just come naturally sometimes. You have to actually train it and practice it.
Very good. Good points. Michael?
Yeah, just like Patrick said, with as Algoma Steel, I mentioned in my video there that as we transition from a coal-fired steelmaking process to electric arc technology, to meet our climate goals and deliver a cleaner, greener future, it's vital for us to cut our greenhouse gas emissions. And I think the stat is something like, with what we're investing in, is removing 900,000 cars off the road. So as we do that, it's important for us to turn to the current students that are the future scientists and steelmakers, to understand from them and bring their knowledge and training to the table, because we don't have that. We've been around since 1901, but that's not what we've been bred to learn. So we're going to really need to focus on students at Waterloo and across Canada.
That's wonderful. It's amazing when I'm listening to you guys. We go from a very old industry to cutting edge industry, and yet all the stuff that you guys have acquired from the university have tooled you to be successful and move forward. And I can't stress enough, like, we have these huge problems that we need to look at. Santa Claus, the North Pole is melting, so the polar ice cap. I'm really concerned about that. So hopefully we can get all these minds together and start trying to find solutions to these problems. Thank you, gentlemen. I appreciate your time. Bill, I'd like to invite you to come do some closing remarks.
Thanks very much, Alan. I think there's no better evidence for the impact of Waterloo than listening to Waterloo alumni. You've had a great exposure to that this evening. The three stories we've heard from Marriage, Patrick, and Mike have been just great examples of what the best of Waterloo is. I've always said the best thing that leaves Waterloo in terms of a product leaves on two legs. And I think we have great evidence of that here tonight. I also want to thank Alan for hosting and moderating tonight. He brings great skill to this with his long years of experience. And I am very happy we were able to catch him before his very busy time with the upcoming Christmas season. I did want to remind you all that Giving Tuesday is next Tuesday. Keep us in your thoughts. And as a last final example of how good co-op is at Waterloo, let me extend my very sincere thanks to Eric Vu, our co-op student who has been our technical support and organizer for this whole project as we have gone through. Thanks very much for supporting us tonight, Eric. Thanks to everyone for coming to our event tonight. This has been a great for me to see all this and to see the participation. And I do hope we get to see you all again soon, whether it's here on Zoom or here on campus. You're always welcome. You're always part of our family. So I hope to see you all again soon. Have a great night. Have a great Christmas. And I hope 2022 is even better to you than 2021 has been. Thank you all.